Hi, and welcome. And here we are with section 1.3, talking about do the numbers make sense and percent increase and percent decrease. So if you're taking a look at this, you can read the warm-up. If the manufacturer wants to be sure that all about the salt content, why don't they just utilize the census to collect data on the salt content? So utilizing a census in this situation, if you think about what a census is, you're using all of the individuals in this situation. So why don't they want to use a census for this situation? For the salt content is because they'd be testing every single chip. Now, if you test every single chip, you're not going to have any chips to sell. So that's a pretty poor business plan with that. So to be sure about salt content, yeah, you don't want to use a census. You can use sampling, and you can get a good read on what your salt content is based on that. The manufacturer decides to 10 bags from each hour's production and measure the salt content in those 10 bags. Identify the individuals, the variable, the population, and the sample in this situation. So if we're talking about the individuals that we're looking at, we're measuring the salt content of the bags. So we're talking individuals is going to end up being the bags of chips. Is what we're looking at. The variable is what we're looking at for the salt content. That's what's going to change from bag to bag, salt content. The population is going to be all bags of chips. And then the sample in this situation is going to be the 10 bags per hour. The 10 bags per hour for that. So breaking it down, individuals, salt content, all bags of chips, and then the 10 bags of chips per hour is going to be the sample. So what we're talking about in this situation is going to be, do the numbers make sense? When looking at data, you always want to ask these questions. You always want to ask, what didn't they tell us? Are the numbers consistent with each other? Are the numbers plausible? Are the numbers too good to be true? And is the arithmetic right? So as you look and as you see reports and as numbers and information is given in the news and in science reports and wherever you're finding information to make decisions on, feel free to scrutinize it. So that's kind of what our job as humans is to look at information and scrutinize it a little bit and say, okay, what's going on with that? Can I trust this data? And hopefully by the end of this class, you're able to look at these and as we work our way through the different units, as to look at stuff like that, reports and data and statistics that are thrown out there, and be able to intelligently scrutinize it and see if it's something that you can trust. So working our way, just a couple examples I have for you here of situations where maybe something's not right, and a couple out of newspapers here that we have. The average office space for middle managers shrank from 151 square feet in 1994 to 142 square feet in 1998. That meant going from a 10 by 11 foot office cubicles to half that size. Well, if you do the math, a 10 by 11 cubicle is going to be 110 square feet. So there's just not a lot that's right about this. And then to cubicles half that size, you're going from 151 to 142. So, it's riddled with inaccuracies. A little bit outdated in the 2000 there, but a Rhode Island newspaper reported 42% of all fatalities occurred on Friday, Saturday, and Sunday, apparently because of increased drinking on the weekends. So, which seems like, okay, 42% and increased drinking on the weekends, that could be. But let's just look at this and look at the numbers. Friday, Saturday, and Sunday are 3 days out of a 7-day week. And if you crunch the numbers and if you look at it, if you crunch the numbers and you look at it and you say 3 divided by 7 is 42% or 42.8%. So really what's happening is 42% of our fatalities are happening on 42.8% of your days. And not to sound morbid, but that's what should happen. You should have about 42% of your fatalities on 42% of the days. So this is not profound information that you're getting there. That's kind of lines up with what it should be. So some more examples, and these are taken out of a textbook, so I'll give you a second to read them, or you can pause the video. I won't give you a second. You can pause the video, and we'll just talk about each one here. So the first one is pretty self-explanatory, and the second one also pretty self-explanatory there. But you know, the skiers are interested in the slopes and the snow on the slopes, not particularly in the town. And then with this second one here, perhaps today's winter storm prevented 20 minor traffic accidents, talking about, you know, how many happen on a typical day. Are the numbers consistent with each other? So you take a look at this and you suspect something is wrong because the numbers don't agree with what we think they should be. You get this barrage of sales in December, and then all of a sudden it backs off. And they have, and you see here, you've got 57 years of data on that, and all of a sudden you've got a huge jump at the end, and then a huge drop-off in January there. Something's not right. So they're cooking the books. They're trying to get that victory one more time, and then taking the loss in January with that. So are the numbers consistent with what you think they should be? Are the numbers plausible? Pretty self-explanatory here with this statement. Replied that the correct figure was about 11,000. You crunch the numbers, you look at that, well, that's a lot of melons per square foot, and as they say, I guess they should grow a stack, or I guess they grow a stack 17 deep. So that's a pretty inaccurate statement there with what they have. Are the numbers too good to be true? So in this case, the suspicious regularity that you have between the two reports, and an inconsistency in animals there is kind of leads to a little bit of suspicion that you have with that one. So are the numbers too good to be true? You're falsifying data, or you're copying data from something else and applying it to yours. Well, that's cause for concern and suspicion. And then is the arithmetic right? This kind of goes back to the Rhode Island, the fatalities one that you look at. And if you look at this, Memorial Day to Labor Day comes out to 26.9% of the year. So the ad claims that 26% of the burglaries occur 27% of the year. You should not be impressed with that. Last piece of the puzzle that we're going to talk about today here is percent increase or percent decrease. A quantity can increase by any amount. 100% increase means that the amount would be doubled. So if you went from $100 to $200, that would be a 100% increase. A quantity can decrease by no more than 100%, and I'm going to put a little asterisk here because you can lose more than 100% of your money. That's called debt, right? So a quantity, so we'll say most quantities can decrease by no more than 100%. But if I had if I had 100 apples and I lost 100 of my apples, I decreased that by 100%, I would have 0 apples. I can't lose more apples than I have. So I can't lose 105 apples if I only have 100 of them. So in this case, you lost all you had. There are some specific instances that, like I said, money would be one that we can lose more than 100% because we can go into debt. But when you're talking about most cases, you can't lose more than 100% of what you have. So here's your percent increase, percent decrease formula here. Percent increase, you've got final value minus the initial value. So you're looking at the difference between the values, you're dividing it by your initial value, multiplying by 100%, or multiplying by 100 to get it into a percent. Folksy way of saying it here that I rather, it's a little easier to think. The new number minus the old number divided by the old number, and then we're going to multiply that by 100. So we'll keep that up there, and we'll take a look at an example. A particular stock price rose from $1,200 to $1,840 in 1 week. What was the percent increase? So we're raising from $1,200 to $1,840. So this is going to be our new number. This is going to be our old number. Just refer to the formula. The new number is going to be $1,840 minus our $1,200. And we're going to take that and we're going to divide that by 1,200. and then you can multiply by 100 to get it to a percentage. So let's take a look. We got 1840. We're going to subtract off our 1200. We're going to divide by 1200, and we're going to be at 53.3. We'll multiply it by 100 to give us 53.33333%. We'll just say 53.33%. Now, this is positive. We can say it's an increase, or just being positive tells you that it's an increase. Now, if you look at this and you say, okay, a 50% increase, well, 1,200, just doing a little bit of mental math right here, 50% of 1,200 would be 600. So if I increased 50%, I would be adding 600, which 50% would be 1,800, 53. This seems plausible, just doing a quick mental math and seeing that. Now, the following week, it fell down to 1,350. What was the percent decrease for that week? Now, the new number is going to become 1,350. Our old number in this situation is going to be that 1,840. So my new number is going to be 1,350, and my old number is going to be 1,840. So we're going to crunch the numbers here. 1,350 minus 1,840 divided by 1,840. Now you're going to look at this and you're going to say, hey, that number's negative. Well, it went from 1,840 to 1,350. So negative 26.63, we'll say. Negative 26.63%. So that is negative. That's a negative value right there. So that's going to tell us that it decreased because we went from 1,840 down to 1,350. So you can say that, or you could say a decrease of 26.63%. So really, the presence of that negative sign is telling me that it's a decrease because you're going down percent. Obviously, the negative sign means that. Or if you'd rather, you can say decrease of 26.63%. I'm fine with either. So that is section 1.3, talking about